All right, so in the previous lecture video, we talked about pressure sensors and microphones. When we make them at microscales, they structurally are similar with some major differences that I hope you have talked about or thought about and then figured them out. In this lecture, we're going to talk about accelerometers and gyroscopes, inertial sensors. And if you look at the number of MEMS devices out there, accelerometers are very close to the top of that list in terms of the number of devices deployed and used. The reason being is that it's a relatively easy measurement compared to a lot of other measurements. Like if you want to measure chemical concentration in an environment, you have to have an opening to the environment. If you want to measure pressure, you have to have a port on your package to let the pressure inside on your device change and measure it. And so on and so forth. So a lot of these sensors need to be in direct contact with the environment in one way or the other. Accelerometers, gyroscopes, maybe magnetic field sensors, these are devices that can actually be enclosed in a package and protected from the environment and used almost everywhere. And for that reason, because of the robustness of these devices, because they need so little from the environment, they're used almost everywhere, right? They make your life easier in a lot of situations. And, the devices that we have nowadays are good enough for a lot of those applications. So the chart here shows the growth in accelerometers. This is early days. It ends at 2013, 9 years ago. And what has happened since then is that the explosion of the application cases and also the number of devices that you need. Mostly because now in every mobile device that you have, there is at least one accelerometer, probably more. In every wearable that you have, as soon as they put some sensor in there, you can almost be certain that they will put an accelerometer in there as well, and maybe a gyroscope. And just looking at how many wearables we have nowadays out there, it just tells you that you need basically at least, let's say, one accelerometer per smartwatch, one accelerometer per a lot of these other smart devices. And you can think about how many numbers we are going to need. In the early days, however, it was the automotive market that dominated because in the 90s, in early 90s, they had the mandate for having airbags in the system in the cars, and you needed something to measure the accelerations or decelerations, right? And that was an accelerometer. Initially, the traditional mechanical accelerometers were used in some higher-end cars, and they're too expensive. You get about, at that time, it was about $300 per axis. MEMS accelerometers came around. Analog Devices was a pioneer in this area, and they could do it for $50 an axis, and then they were much smaller and they were much more robust, and they didn't need testing and calibration all the time. And they actually needed some of that, but all of that was done on chip. So that was the main driver for the MEMS the accelerometers. It was good timing. That was the initial days of MEMS as well. And but as we said, when you get to the 2000s, early 2000s, mid 2000s, it was the cell phones that and other mobile devices that started to utilize more and more of these accelerometer devices. The main reasons that we're using accelerometers everywhere is that first, they are low cost. A typical accelerometer that is good for, I would say, 80% of applications in consumer area is less than $1, including the electronics with digital output and all the compensations that is required. Package sizes are tiny nowadays, right? Even in some cases, they don't even put a package around the MEMS device. They just sell you the die. But nonetheless, the packages are on the order of millimeters on a side nowadays. And from that kind of a package, you still get information about 1, 2, or 3 axis acceleration, and in some cases maybe angular rate as well. And another reason, and actually one of the more important reasons that accelerometers are used in almost every situation that you have some sensors, is that they are very low power devices compared to a lot of other sensors. Nowadays, accelerometers consume microamps and then give you meaningful data for that such low levels of current, while a lot of other sensors actually need significantly more. Even gyroscopes that are needed in many navigation applications, for example, and they're used in combination with accelerometers. Usually you're talking about milliamps versus microamps for accelerometers. So accelerometers do not have to be in touch with the environment, so they're fairly robust, they're low cost, they're low power, they're small. They tick all the boxes that you maybe thought about before we took this course about MEMS, about these microelectromechanical devices. And, as a result, they're actually quite common in different applications. Now, when you look at the accelerometers that are out there, MEMS devices we're focusing on, there are a couple of different approaches. We'll show you some examples about each one of these. You usually, one of the most important distinguishing factors is that whether you have a single chip accelerometer or a multi-chip accelerometer. A multi-chip accelerometer is one where you make the MEMS device on a piece of silicon and apply all the protection that is required, and then the electronic chip that receives the signal from the MEMS chip is put next to it inside one package. From the outside you don't know it, you don't notice it. If you look inside, you see there is an electronic circuit and there is a MEMS chip. Single chip devices, they integrate MEMS and electronics together. Well, the dual chip or multi-chip approach gives you the ability to use optimum processing steps for both electronics and MEMS. The con is that you pay more, right? So you have to pay for two chips. You have to do a little bit of extra processing, wire bonding between the two chips. But because you're using optimum processes, you may have better yield in both of them. You may have better performance, especially on the MEMS side. And therefore it may be worth it. Versus a single chip approach makes the MEMS and electronic circuit on the same chip, and in this situation you can save in cost. If your MEMS device has a high yield and your electronics yield is not affected that much by including a MEMS device on top of your electronic chip, you can potentially have a lower cost solution. However, there are compromises, right? So you cannot have the best MEMS device or MEMS technology for your mechanical component because, for example, you cannot have a 100 micron layer or 200 micron layer of polysilicon on top of your CMOS chip. It's going to destroy the CMOS. And maybe on the electronic side, you have to have this compromise that you cannot use the latest technology. You want something robust that can basically survive a few post-processing steps when you're making the MEMS device. So there are pros and cons to both approaches. In terms of transduction, it's almost entirely capacitive nowadays. You have in-plane capacitive devices, out-of-plane capacitive devices, bulk micromachining, surface micromachining, but in vast majority of these cases, the transduction mechanism that you use to measure the acceleration is capacitive. We'll talk about that in a second. And there is one exception to that. It's a thermal accelerometer where we actually use heat to measure acceleration. This is an ingenious solution, and I'll talk about that a bit later. But spoiler alert that this was an SFU invention, and the professor at SFU that developed this device actually, it was a commercial success, and he benefited from that. But the idea, the initial implementation, the patenting, the licensing, all of that happened at SFU. And then we talk about accelerometers. If you go back historically, it started with piezo-resistive devices. Back in the early days of the MEMS process development or technology development, it was easier to make piezo resistors than capacitive devices because of the limitations of fabrication technologies. Basically, we didn't have DRIE back in the early 80s maybe. And for that reason, we had some piezo-resistive devices. Some of them are still produced because of compatibility that you want to have in a line of product. But as I said, the vast majority of the devices are now capacitive. A small portion of devices are piezoelectric. They use piezoelectric transduction. The reason that, we mentioned that nowadays we have more service providers that have a piezoelectric layer in their process And these service providers, if you want to make a piezoelectric accelerometer, they can do it for you. The challenge is that most of the acceleration sensing that we want to do is at low frequencies. And as we mentioned before, well, piezoelectric sensing is not necessarily good at low frequencies. We have this challenge of charge leakage on the charge capacitor. Now, if you're smart about it and go and figure out a way to do, let's say, your measurement at high frequencies, even though your input signal is at low frequencies, you have a solution, and then you may be able to use piezoelectric sensing that way. And again, think about it. How can you do that? How can you do a measurement of, let's say, a very low frequency acceleration signal at, let's say, 1 megahertz? So think about it, and there is an obvious answer here. I'm hoping that you guys can get to it before the live session. If not, let me know, or check your answers with me in the live session. Now, applications of accelerometers, well, the obvious one is measuring acceleration. This is really, I think, goes without saying, but think about cases where you need to measure acceleration. There are not really too many cases that you need to measure acceleration. Usually you want to measure something else. But nonetheless, measurement of acceleration is something that accelerometers do. Navigation is where you actually need to know acceleration. So this is where the application is. You want to, let's say, without using a GPS signal, you know what is the engine that is driving this item forward, and if you measure the acceleration and angular rate, you should be able to find your location in a space if you know your initial coordinates. So that's the idea. In practice, things are a bit trickier. Crash detection, deceleration sensing, all these things, again, require the use of an accelerometer, but in this case, you're basically not monitoring accelerations, you're just monitoring that threshold, right? You want to know if you exceed that threshold to deploy the airbag, for example. In a similar situation, you may want to use accelerometers in a car, for example, for stability control. And in that case, you want to know the acceleration. It's not threshold-based. You're actually monitoring what is happening at, let's say, the driver's side front versus, I don't know, the back of the car, and try to keep the car in a straight line if necessary, right? Image stabilization is another application area for accelerometers, especially DSLRs, the large cameras. You want to make sure that the vibrations of hand are removed from the picture, so you get better quality images in video or video cameras or pictures. And you want to move either the optical elements or the sensor itself in response to your whatever that is moving the camera, right? So it could be the shaking of the hand. And vibration control, actually image stabilization, just another example, could be on a drone, right? So you have a drone flying around and it has a camera that is taking images of or recording video of something, and you need to make that as stable as possible so that your image is not moving up and down all the time. Vibration detection is another application area for accelerometers. So in this case, we are interested in knowing about what is happening in this environment in terms of vibrations, not just vibrations are essentially like high frequency acceleration. So you can think about it as the difference or the distinguish we made between pressure and acoustic signals. So pressure changes are low frequency. You're talking about maybe a few hertz at most. But acoustic signals are high frequency. Same thing can be said about acceleration and vibration. Acceleration changes are usually low frequency. You're talking about less than 100 hertz or so, maybe even less than that. And anything above that it's still acceleration, but you can think about it as vibrations. It's cyclic, right? It's going up and down. And there is more, right? So you can measure angles. If something has a tilt in it and you have an accelerometer, you can use the g-force of the Earth as your reference, and you can measure your tilt with respect to that vector, machine health monitoring is usually done through listening to the acoustic signature or vibration signature of your device, your system, and notice the changes in it, and then hopefully do some predictive maintenance or figure out what is the source of some fault, or just maybe even detect the fault. Seismology is an up-and-coming application area for MEMS accelerometers. This is where we want to listen to or detect vibrations of Earth, right? And these are usually low frequency and small in amplitude. You're talking about micro-G level signals here that are below 50 hertz in vast majority of the cases. And measurement of low amplitude, low frequency signals is a tricky business. But MEMS devices are getting so good that they can do that kind of a measurement. And then finally, acoustic measurements. And then acoustic measurement, you can think about it in two ways. It could be vibrations caused by an acoustic signal, or your accelerometer is sensitive enough that it can actually measure acoustic vibrations of air molecules. And we actually, in our lab, in our research lab, we have accelerometers that can do that. They have a bandwidth of about 5 kilohertz and a sensitivity of less than a micro-G per root hertz. And these devices, when you talk at this end of the room and they're located at the other end of the room, they pick up your voice through the vibrations of the air molecules that, caused by somebody speaking. The reason that I want to use an accelerometer instead of a microphone in that application is that the microphone will just tell me that there is somebody in this room speaking. It doesn't tell me where that person is. With an accelerometer, if I pick up that, actually I need two accelerometers, but if I pick up an acoustic signal, I can actually say that this signal is coming from that direction. And the acceleration is a vector versus the intensity of pressure that the microphone picks up is just a scalar quantity. Okay, moving on. A typical accelerometer, MEMS accelerometer, is a mass spring system. You usually have some sort of a damping mechanism around it. It's usually viscous damping, the air molecule, friction with air molecules and then their impingement on the surface. The exception here is the thermal accelerometer that I'll talk about it in a few slides. So what happens in the basic structure that is shown here is that once you apply an acceleration to this structure, it's usually applied to the frame. Your proof mass is suspended above the frame, above the package. The acceleration is applied to the frame, so therefore there is a force on that frame. Inertial force ma, Newton's law, right? And then that force causes the displacement of a proofment relative to frame, and how much displacement is, how much that displacement is determined by the spring constant that you have here. So there's going to be a force ma, and that force is balanced with the restoring force of your spring, k times delta x. Okay, so k times delta x from your spring, ma inertial force, and what you need to measure is that delta x and figure out what the input acceleration was. So if you look at the formula at the end, you have a relationship like this. So x, or delta x, is m over k times the input acceleration. If you look at it in Laplace domain and write the transfer function, you can see that any frequency you can come up with a transfer function like this, h of omega, which is the displacement of the proof mass over the input acceleration, the absolute amplitude, is given by this expression. And as every other second order system, you have a resonant natural frequency in this case, and damping, which are given by these two expressions here. And what you can see is that at DC, when the frequency is very, very small, the displacement over input acceleration is just m over k. So it's ma over k delta x. Remember, that has to be 1. And if you go back to your dynamic section, this is equal to 1 over omega naught squared. If you remember, the natural frequency was square root of k over m. So right there you have a problem. You can see that if I want to get a large delta x, and look at this, there's really nothing here beyond having a spring and a mass. So if we can reduce the model of our system to an effective spring and an effective mass, this equation applies. What this says is that if you want to have a large displacement for a given acceleration, so a large displacement makes it easier for me to measure it and then make my life easier, basically higher sensitivity, omega naught will be small. And what that means is that the bandwidth, the range of frequencies that I can do the measurement will be fairly narrow. On the other hand, if I want to have a wide bandwidth sensor, the problem is going to be that the displacements that I will get for a given acceleration are going to be, with the square of that frequency, proportional inversely to the square of that frequency. So this right there is one of the challenges with designing MEMS accelerometers, right? You're talking about sub-nanometer displacements, and how do you measure that? You have bulk micromachine devices and surface micromachine devices. Again, if you go back to the fabrication sections that we discussed, the processes had their own pros and cons. When you use these two different approaches to make a bulk micromachine device accelerometer versus a surface micromachine accelerometer, here are some, let's say, relatively straightforward outcomes. When you do bulk micromachining, you have access to the entire substrate or a very large mass over there. What that gives you is a large proof mass means that you can have lower noise, more sensitivity. That MA portion is getting larger and larger, right? So you can have a lower noise device. However, when you do surface micromachining, usually your thin films are only a few microns thick. Therefore, your mass will be small, and therefore your delta X's for a given acceleration are going to be small. But the issue here is that for a surface micromachine device, you have some additional benefits that I'm going to talk about in a second. For bulk micromachining, you have to go and usually do some sort of anisotropic etching of silicon. You remember, you're going deep into silicon, so it has to be anisotropic. If you're using KOH kind of a solution, wet etch, you get those side walls, but nonetheless you can go very deep, but the lateral etch will be limited. Nowadays we don't do it. We don't use wet etching for deep etches. We use DRIE. Which is again anisotropic. On the surface micromachining side, well, you don't have such thick layers of, let's say, structural layers, and therefore, yeah, you still use DRIE, but it's only for 5 microns of polysilicon versus, let's say, 200 microns of pure silicon, crystalline silicon. But what you gain on this side is that, well, the process may be a bit easier for the etching of the materials, but also, you have the possibility of integration with electronics. If you're doing bulk micromachining and you're doing all sorts of deep etches into the substrate and all that, it's not easy to integrate any electronics when you have so much variation in topography on your wafer surface. With surface micromachine devices, that's a bit easier, so you can actually put some electronics next to your device. And for all of this stuff that we said, bulk micromachine devices are usually reserved for high performance applications where you need something usually well beyond what the consumer needs, and consumer market, I mean. And then surface micromachine devices are used for almost everything else, right? So these are, compared to bulk micromachine devices, they have lower performance, but they're much cheaper, and they can be made much smaller, and therefore, cost wins. If you have a low-cost option, usually in a lot of these situations, that's all that matters. Piezo-resistive accelerometers, as we mentioned, were the initial devices, and what we had was a proof mass and some sort of a beam spring mechanism to hold it in place. So this is a suggested fabrication process for this device, and we would put the piezo-resistors at the base of these beams so that we could measure the accelerations with, or the deflections of the proof mass this way. We have done examples of this before. So what happens in this case, instead of measuring the actual displacement of the proof mass, we look at the stress that is caused at the anchor because of the displacement of that proof mass. And then once we measure the stress, we can relate it to the displacement of the tip and therefore the acceleration. As I said, these devices are not that common anymore. Instead, almost all devices, at least around you, are capacitive type accelerometers. They measure delta X by measuring the changing capacitance between some fixed electrode and some electrode that is attached to the proof mass that is moving up and down. Now, in terms of how you can do it, well, out of plane is one possibility, right? So for that same piezo-resistive structure, if I put an electrode on top of that proof mass, I can measure the delta X directly. I can have two electrodes in plane that are going back and forth, right? So if it is in plane displacement, I can measure it with two parallel electrodes. But as we saw before, usually the capacitances you get from two electrodes is small, so we use a comb in most situations in order to increase the capacitance, or the DC over dx factor that we saw was important in actuation and also sensing for electrostatic devices. In some cases, you may want to have your device, the mechanical device, works based on torsion. So what you can do is that you can make a capacitive device, and then if this plate is tilting in and out of plane, you can measure a change in capacitance. So here is an example. This is a high-performance accelerometer on the left. On the right, it's an early accelerometer developed in actually early 90s, once people figured out how to do surface micromachining. This one on the bottom right is a torsional one, so you have comb fingers, interdigitated comb fingers, but the proof mass can actually tilt in and out of plane. And this is a special case. We didn't look at this case when we talked about comb drives, but the equations are not really too hard to drive. Anyway, nonetheless, another application of capacitive sensing here. And this is another one that has an out-of-plane capacitance change between a fixed electrode on the substrate and a proof mass hanging with a couple of beams. So some examples from the industry. Analog devices, as we mentioned, was a pioneer in the field, especially in the early days, automotive airbag days. ADXL50 was a device that basically captured the market at that time for airbag deployment. And this was a single chip device. You had the MEMS and electronics inside one package. As you can see, the MEMS part is actually relatively small compared to how much you needed for the electronics, right? So in the electronic circuit, you need the amplifiers to detect the motion, you need oscillators. We'll talk about the way they did this capacitance measurement in a couple of lectures once we talk about interfacing. It was made in a bi-CMOS process, meaning that the electronic process doesn't really matter that much. Could make bipolar devices and CMOS devices at once. I think they use mostly CMOS anyway. And this is the schematic of the device. Again, we have capacitive combs here. This is your proof mass that goes to the left and right. You use beam springs to hold it in place. And once an acceleration comes, this proof mass goes either to the left or right, depending on the direction of the acceleration. Each finger that is attached to the proof mass is surrounded by two fingers that are on the substrate. They are not shorted to each other, two different fingers. And once, let's say, the proof mass goes to the right, the capacitance between these two will increase, and the capacitance between these two will decrease. It gives you a differential signal. One C goes up, one C goes down, and you make a differential measurement that way, like this situation shown here. So this is your moving finger, and these are the two fixed electrodes. And then the rest of it is just an amplifier and then a demodulator circuit, which we will talk about, as I mentioned, in a few lecture videos. So top view looks like this. Again, as I said, you have a moving finger. So this long one here is your moving finger, and then you have two fixed electrodes that you use to measure the relative displacement. From the side, the anchor area for each one of these electrodes looks like this. So they're basically a little bit above the surface. Bosch is another major player in the accelerometer area, actually any type of MEMS microsensor area. And they often have a two-chip solution. So in this case, what you can see is that this is an X-ray image of the device. You have a MEMS chip. One accelerometer here measures the acceleration in X direction, another one in Y direction. And this is a MEMS chip, and it is wire bonded to an electronic chip, right? So these are bond wires that connect the electronics to the MEMS, and then the output and the power supply for the electronics are connected to the package. So if you open it up, you see this. So this is your MEMS chip, and the MEMS chip is like this. You have your MEMS device right here that is fabricated on this bottom wafer. Then you put a cap wafer on top of it to create a small cavity here to protect your device from everything else that can happen to it. And you put this inside the package, this combination inside the package, bring out the contacts to the MEMS device through this cap. So this is these guys here, and then connect them to your electronic circuit, to your ASIC, application specific IC. So that's that. And then if you want to measure more than acceleration in more than one axis, you can actually start putting multiple accelerometers inside one package or on one die. So in this case, if you look at this one, you have an acceleration for the measurement of, you have an accelerometer, a proof mass for the measurement of accelerations in X direction. Well, look at that. This is like a 90-degree rotated version of the same chip on this corner. This is for measurement of accelerations in Y direction. And then they have one other proof mass here for the accelerations in Z direction. Right? So basically, these are three accelerometers in one package. And these are top, side, and cross-sectional views of the structure. One interesting thing about this process by Bosch is that they deposit a 20-micron layer of polysilicon and etch it using DRIE. 20 microns of polysilicon is quite a bit. You know, this is a surface micromachine device if you think about it now, but they have pushed the thickness of the layer to about 20 microns. Now, so these are some specifications. I'm not going to spend so much time here because these things change all the time, right? And especially in the earlier days, 10 years ago or 15 years ago, these things were improving all the time. And nowadays, we are getting close to the physical limits or practical limits for many of these performance issues, and things have slowed down. So nowadays, companies make new accelerometers or bring a new accelerometer to the market, they probably spend more time on the electronics and signal processing inside the electronics than on changing the MEMS side. The MEMS side is probably close to the edge of the fabrication capabilities that they have. So here's another example from Freescale. In this case, again, you get a single chip, 3-axis accelerometer. However, the difference is that, well, the similarity is that it's still a two-chip solution, right? So if you take an X-ray, you'll see that there's a MEMS chip here, a bunch of bond wires going between the MEMS chip, and then an electronic chip on the left side. And if you take a cross-section of the package, you'll notice the same thing, right? So you have a MEMS chip with the cap and all that on the right side, and then your ASIC on the left side. The difference between this device from Freescale and the one from Bosch is that they're doing the 3-axis measurements, acceleration measurements, with one proof mass. So instead of having 3 accelerometers in parallel, what they've done is that they have put one big proof mass in the middle of the chip. They have provided springs that let it, or the beam spring arrangements that they have will let the proof mass to go up, down, left, or right. So it can actually move in all directions, all 2 directions in plane or out of plane. And all of that is done applied to the same proof mass. How do you know which one is which? How do you know if the capacitance changed? Is it because of a Z acceleration or X acceleration or Y acceleration? They do that by proper arrangement of the electrodes around this. So they have some electrodes that only measure the up and down displacements, and they have some electrodes that only measure left and right displacements, and then probably something underneath the proof mass to measure outer plane displacements. Now, that's one thing they did, but this is a surface micromachine device. They didn't have a 20 micron device layer as Bosch did. So here's another smart thing they did. They put a bunch of weights onto the proof mass. These are aluminum weights that basically, by putting weight, I mean that they deposited a layer of aluminum and patterned it properly so that at the end of the story you're left with these extra weights on your proof mass. And this way they increase the mass of their proof mass. Remember from that formula we had that the sensitivity is m over k. Well, the k part, the spring constant part, you can design through mechanical engineering and figuring out what you need for the beams or putting more of them in series. The m part is still important. So if you increase the m, your sensitivity goes up. And this is one way of increasing the m. And here is a close-up value of that weight, these aluminum extra weights that they have on the plate, and this is a cross-sectional view that you can see that they deposited a sacrificial layer and then released it at the end of the process. Another big player in the accelerometer market is STMicroelectronics. I'll just go through this a bit more quickly. There's a lot of similarities between all the offerings from these companies. So just sticking to the interesting parts, here's an example. It's a 3-axis accelerometer, 3 millimeters by 3 millimeters by 1 millimeter. That's the package dimension. And this was used in iPod Nano, right? So this, we're talking about, I don't know, 10, 12 years ago. And at that time, the size of this device was a major winning factor. Go back to what we talked about on ADXL50, one of the initial accelerometers. And the die size, the silicon part for that device was about 3 millimeters by 3 millimeters. Now, you put that inside the package and you get a package that is, let's say, 5, 6 millimeters on the side. In this case, the package is actually that big. Yeah, let's just move a little bit quicker through this. I want to start the discussion on gyroscopes after this, but one note here, quick note here that you can see in this case again, you can make a 3-axis accelerometer using a single proof mass and having a proper design of the beams and all that. But that design is challenging, right? At the end of the story, you really cannot make that system to be insensitive. So if you have an acceleration in X, your electrodes in Y may also pick up something because of this cross-axis sensitivity that you may bring out, or you may let's say, make worse by the design of these compliance mechanisms on your structure. So the cross-axis sensitivity may hurt you and be so much that you give up the idea of a single proof mass device. Here is an example that they have actually 2 accelerometers inside the package. So they do X and Y measurement with one proof mass and then the Z measurement with a different proof mass. Now, all these devices we saw so far are, following the model that we showed at the beginning. It's a mass, there is some spring mechanism, and damping is from the gas in the environment. The challenge with all of them is that you need to do that MEMS processing, right? So you need to create, let's say, those narrow gaps that you need for capacitive detection. You need to create those beams. It's a delicate micromechanical structure, which can, as a result, break easily. Now, here is a vastly different idea for measuring acceleration. The idea is that, well, instead of measuring the displacements of a solid proof mass, let's do it in gas phase. How? Let's put a heater somewhere and inside a gaseous environment and turn it on. once you turn it on, you will have a temperature distribution. So if you look at, let's say, two sensors at a same distance from this heater, you will have a temperature that is the highest at the heater location and drops off as you move away from it. And if those two sensors are located at equal distances from the heater, they should measure the same temperature, right? So they measure the same temperature. You know, let's say if the heater is at 100 degrees, they measure 50 degrees Celsius. And now what happens here is that the heater here will heat up the air or the gas above it. As you apply an acceleration, as the gas heats up, its density becomes smaller. So when you apply an acceleration, the more dense gas, the cool gas, will respond more strongly to that acceleration and displace, well, they move a bit more than the light gas, the heated gas, the hot bubble that you have. And therefore, you get a temperature difference. When you look at these two temperature sensors, if you apply an acceleration, now they measure a difference in temperature. One of them may measure 50.1 degrees, the other one may measure 49.9 degrees instead of, let's say, 50 before. And this is an ingenious solution. Why? Because look at this. There is no moving element. You just have a heater and two sensors, and all of them can be fixed to wherever they are. There is no movement. There is no relative movement. The movement is happening in the gases phase. So this idea is an SFU invention by Dr. Albert Leong from the School of Engineering Science. He has since retired. He retired, I think, a couple of years ago, and enjoying his retirement with the after this great invention. The idea was licensed by Analog Devices. This is back in, I think, late 90s. And the reason they came and licensed this out of SFU is that at the time, this was offering a performance that was similar to their own accelerometers. And this was a significantly simpler device. You just have to make a heater and two temperature sensors, and both of them are really easy to make using MEMS technologies. And the performance was as good as what they had using a much more sophisticated technology. So they came and licensed it from SFU. They later on spun it off as a separate company, MEMSIC. You know, if you look for the stock key MEMS, that's this company, MEMSIC. And it's a much, much bigger company than what it was before, but this was their first product. They made the company based on this idea. How does it look like on chip? This is really it. What you have is a heater, which is just a line of metal that goes back and forth, maybe two of them in here. And your sensors are exactly the same. You're using a thermistor, a metallic resistor to do the measurement of heat or temperature, and you have a heater that essentially has the same structure in the middle. You position them at the equal distances, get rid of the silicon underneath because you don't want the conduction through the silicon, thermal conduction through the silicon messes your life up, and you have a really great accelerometer. And this is Dr. Leong with one of his chips. So the advantages of these thermal accelerometers: no moving part. So these are extremely durable. Basically nothing can break them, you know, because the heater and the temperature sensor are just so light that no G value is going to damage them. It's a simple device. You just need a heater and a temperature sensor. Both of them are easy to make once you have a conductive layer. And they're inexpensive as a result of all those benefits that we mentioned so far. However, there is no free lunch. So with all those good things that these devices have, well, there are some cons. The disadvantages include power consumption. As soon as you talk about having a heater and producing heat, well, you can think about it as wasted power. So MEMSIC devices typically consume milliwatts of power. Back in the early days, that was okay. That was as good as a capacitive device. Nowadays, that's not competitive, right? You're talking about microwatts for capacitive devices nowadays. They have dropped their power consumption significantly as well, but there's a limit. You need a special packaging. That's another drawback, right? So what happens is that you need to make sure that you have a stable environment around your heater and your temperature sensor, so that let's say the gas pressure inside there doesn't change, or the gas composition doesn't change. And then in order to improve your sensitivity, you want to fill the package with a special gas, not maybe nitrogen, but something a little bit heavier like SF6. And finally, you had an issue with bandwidth. These gases don't respond to fast accelerations, and therefore, they were not good for measuring fast changes in acceleration. Nonetheless, they made and sold millions and millions of these devices. And here's a photo of this device. So what we have here is the heater at the center, and now this is a 2-axis device. So they put temperature sensors on the right and left, and then top and bottom of this. And depending on where that hot bubble moves, you can say, if your x acceleration was this much and y acceleration was that much or not. And they actually later on made a 3-axis accelerometer as well, again using the same idea, but it worked best in 2 or 1 axis. As you can see, super simple fabrication. You just did a post-processing step to get rid of the silicon underneath. As you can see, for example, here, your electronics doesn't really take too much room now, because it's a simple driver circuit and a detector circuit. And this thing was really special in terms of the idea behind it, that this was such an innovative idea, such a different way of looking at things that could actually beat the typical devices at the time. Now, these are the typical requirements. This is a little bit old, about 20 years ago, from a special issue from the proceedings of IEEE. But the characterization and the division that it made still holds. So, when you look at accelerometer performance metrics, you can have navigation-grade devices, automotive-grade devices, and even other classes. And you can see that there could be a significant variation in terms of the performances that are needed. So for example, for navigation, you need less than 4 micro-G of resolution. Automotive, 10 milli-G or more is good enough. This is not easy, right? And then, that was not easy back then. It is still not easy right now. But anyway, and you can go and have a look at that paper from '98, already 20-something years old. But I'm sure with what you learned in this course, you can actually follow most of the material in that article. Now, accelerometers are half of what you need in navigation, half the information that provide you with half the information you need for navigation. So they tell you the linear acceleration values. For proper navigation, you also need to know the angular rates, the changes in, let's say, along the axis, around the different axes of motion, and so on and so forth. So like acceleration that you have 3 axes, x, y, and z. For angular rate, you can also have pitch, yaw, and roll, depending on which angular rate you're interested in. And the way to measure that is using a gyroscope. Micro machine gyroscopes are almost exclusively use a vibrating element to sense rotation through Coriolis force. So what is Coriolis force? Coriolis force says that if you have a subject that is sitting on a rotating axis, and this person looks at a particle that is traveling in a straight line with velocity v, vector v here, this person will see an apparent Coriolis acceleration applied to this particle. They see, so think about it, that if this is rotating, if you're sitting on a system of axes and it is rotating, and you look at this particle that is moving, you think it's basically getting farther and farther from you. It is an apparent acceleration, it's not a real force. But if they want to model it with respect to their own system of coordinates, they would say that, okay, it is as if that person or that particle is subjected to this force. What is this force? Well, it is the mass of that particle times the velocity of this particle, cross product of the velocity and omega, the rate, the angular rate that you have here. Now, if you have that apparent force applied to that subject, you would see a displacement, an apparent acceleration, right? And that's it. That's Coriolis force. Now, in MEMS, we cannot have a particle that is moving continuously, right? So we cannot have a V that is basically going all the way. Your package is rotating. Let's say this is the package of your gyroscope. It is going around this axis. You cannot have a particle that goes in a straight line. So what happens in MEMS cases is that you have a particle that goes back and forth. And then now, if the package rotates, this keeps going back and forth. And this, for example, could be like a tuning fork. Right? So you have a resonator, and then this is going back and forth like this. And I monitor the apparent acceleration or movement of these tips. Now, for omega now, for V, I have an oscillatory motion, right? So it's a cosine omega t. It's going back and forth like that. And then I will have, therefore, remember, this is a cross product. So if this is the V and I'm rotating it, I will see a force perpendicular to that. So let's just have a look at a simpler diagram here. What I can do here is, let's say, I can bring this mass into oscillations along the x-axis. So I call it the drive axis, right? So this is going back and forth around this axis, around this orientation. Now, if you rotate this structure, the frame and everything included, you will have an apparent force in the normal direction. Remember, it was the cross product of the V, which is the vector in this direction going back and forth, and then your acceleration is rotating the whole thing, so you'll get a force in this direction, in the y direction. So your drive is in x direction, your rotation is around z, your displacement or your force will be around the y direction. If I measure that displacement in the y direction, I can figure out how much that omega was. Now, in this case, what I do is that I go and make two high quality resonators. Why high quality resonators? Quality in this case means quality factor, right? So I want to have a really sharp peak. Remember that Q effect in dynamics? I want to have a really sharp peak. Why do I want that? For the drive part, I want to use the smallest signal to cause the largest displacement of this proof mass in this direction. So I want to get as much displacement as I can get, right? So remember that force was 2mv omega. So I want to get the largest V that I can. And also, the proof mass, once I design it, that's it. So Q factor is going to help me. If I design it with a Q of 10,000 for a given force, I will get 10,000 the displacement that I would have at DC. On the sense part, I also want to have a high Q device. Why? Because if this device is vibrating in this direction and I apply a rotation here and then I start to get a wobbling of this device and then this is going up and down and I want to measure it, I want to measure it most efficiently. When does that happen? Well, I have a small force, small Coriolis force that is moving this M up and down. Well, I want to most effectively convert that force into a displacement. And to do that, I would like to have a really, really large Q. And therefore, I would want to have a high Q resonator for the sense mode as well. Well, if the two modes are not exactly the same, I have a problem. Now, I'm driving it at a frequency. I don't have a problem, but I could do better if the two are not on top of each other. So if this Q is, let's say, 5,000 and this one is, let's say, 3,000, and I excite it here, this is where my force is going to be. This is my sense amplitude. But if I could put these two peaks on top of each other, I would measure that much larger signal for the same input, right? So that is an issue in MEMS problem, the MEMS oscillator, MEMS gyroscopes, that there is going to be a mode mismatch. The resonant frequency that you have in X direction could be slightly different from the resonant frequency in the Y direction. That's a mode mismatch. These are two different vibration modes of the same structure. And when you're designing these MEMS gyros, you want to put these modes as closely as you can on top of each other in terms of frequencies. One is in X, one is in Y, but you want the frequencies to match. And usually, actually, as it turned out, it's not that easy. You know, fabrication tolerances, all sorts of non-idealities will separate these two modes from each other, and maybe you have to apply a little bit of feedback signal to make them match. Gyroscopes are, again, divided in different categories: rate grade, tactical grade, inertial grade. And for inertial grade, it is basically a gyroscope that should be able to basically guide you in space. You know, once you have the acceleration data and the rate data, you should be able to figure out where you are. And for those devices, you have to have a very small angular random walk. What this is that it's a very small change, a very slow change in the output of your gyroscope. So you're measuring, let's say, in this case, for a rate grade accelerometer, let's say half a degree per hour. So you see this signal going up and down. And it's called random walk. You really don't have that much control over it. But for an inertial grade device, it has to be less than 0.001 degrees, right, per hour, per root hour. It's kind of a noise. And we'll talk about noise in 2 or 3 lectures. Bias, drift, all those other issues, again, the situation is tighter and tighter as you want to do navigation with these devices. MEMS devices right now are mostly good only for rate grade applications, right? So for tactical grade and inertial grade, we don't have good MEMS gyroscopes yet. For tactical, there are some, but inertial grade, we still have to wait a bit more. So what are the challenges of designing MEMS gyros? Well, one is that you need to have 2 high-Q, high-performance devices that are matched to each other, right? So the resonator in X direction and the resonator in Y direction, not an easy task. The Coriolis force is tiny at the end of the story. Remember that V that you have for 2mv omega, right? The mass is small, the V is small. The Coriolis force is going to be small. And if you have a device that, let's say, has a 1 micrometer drive amplitude here, on the sense axis, you measure an amplitude of less than 0.01 angstrom. That's on the order of the diameter of a hydrogen atom. And that's tiny, right? Cross-coupling between the drive and sense can actually make your life hard, because remember, look at the relative values of these two. One is 10 to the minus 12, one is 10 to the minus 6. So a 6 order of magnitude difference in amplitudes of these signals. You can think about the drive signal in terms of the electrical drive signal, that it is much larger than what you have on the sense side. So the interference can be significant and make it hard. And all potential manufacturing issues, like asymmetries in your etching processes for whatever reason. If your device is at the corner of a wafer, maybe your DRI is not etching it straight, right? And that creates a little bit of asymmetry and things like that, right? So gyros are MEMS gyros. We have a lot of them around, but they're still, at least in terms of performance, there's still hope for improving their performance. We still would like to have much better devices out there, and it's still an active research area, very active. So some examples. This is an early example from '93 of a tuning fork gyroscope. So we have 2 resonators that are coupled to each other. That's a fabricated device. And then back then you can see that the finite element simulation was a 2D, relatively simple simulation. An alternative to this design, where I have two resonators that are moving in plane, is a vibrating wheel gyroscope. So in this case, what I have is a wheel that is rotating, well, let's say in the initial case. And if you have a rotation along the x or y axis, the wheel will tilt, right? The wheel wants to maintain its angular momentum, and it will tilt relative to the substrate. Well, again, the challenge here for MEMS devices is that you cannot have continuous rotation. So what you will have is back and forth rotation. And then your wheel, that wheel that you make using MEMS technology, is if you have an angular rate applied to the x or y axis, it's starting to wobble. So it's just going up and down, essentially creating a differential signal for you. How do they look like? Something like this, right? So you have your drive circuits here, and then you have your sense electrodes underneath this structure. Now, going back to our CVGs, let's just look at some numbers, just to put things into perspective a bit. ADXRS 150, this is a relatively old device, at least for 10 years ago. But look at the numbers that we have in terms of performance. The full-scale capacitance change for this device is 120 autofarads. So that's 10 to the minus 18 farads. How much is it? Well, if you put one electron on these capacitors, you will measure a point. If you put one electron on these capacitors, you measure almost a 0.1 millivolt change. That's significant, just one electron. But that's full scale. The detectable capacitance change is 12 zeptofarads. Zepto is 10 to the minus 21. So now, if you want to think about that capacitor, if you put one electron on a capacitor that size, you will produce a 10 volt voltage difference between the two electrodes of that capacitor. Detectable movement for the sense mode is 16 Fermi, and this is again, I think, a unit that is probably not familiar to a lot of you. 1 Fermi is 10 to the minus 15 meters. So 16 Fermi is 10 to the minus 14 meters. That's significantly less than the diameter of a hydrogen atom in the classical model. So, and then the bandwidth is 1 kilohertz for this device. So, you're dealing with really, really small numbers, especially for gyros, and then that's one of the reasons that they are still a challenge to make a good gyro. And then, the structures, again, we have usually a 2-chip solution for gyros. You make the MEMS solution, the MEMS device on one chip and the electronics on another chip. Or alternatively, you can combine MEMS and electronics in one process, in one chip, but you lose a little bit of performance on both sides. So here's an example, ST Electronics, ST Microelectronics. This is a vibrating wheel type of a device, so you have the MEMS device at the top. This is the wheel that is going back and forth, and then you have a bunch of electrodes underneath to detect the wobbling of that wheel when it is subjected to angular rate. And yeah, so here's another example. Now in this case, we have one of these rotating wheel type of gyroscopes next to an accelerometer. So this is one chip or one package that gives you acceleration as well as angular rate information. Here is another example, a 6 degree of freedom IMU, so it measures the acceleration and angular rate along 3 axes. So it measures rho, yaw, and pitch for the angular rate and acceleration in x, y, and z. So what we have here is a 3-axis accelerometer here at the corner of this. This is one chip at the corner of that package, and 2 gyroscopes, a 2-axis gyro and a single-axis gyro over here. And then, how we make these devices and then how to save space. You can stack the chips on top of each other, so you can put your electronics right on top of the MEMS package and make it a little bit, lateral dimensions a bit smaller. You can put them side by side as you've seen so far. Depending on where these companies feel their most competent, they may use different approaches of fabrication here. This is an interesting device. It's a vibrating ring device. Now, the idea here for this device is that I have a ring, and instead of having a proof mass that has a set of springs in X direction and a set of springs in Y direction, I have a ring, and it has two vibration modes. So it has a vibration mode where I have, let's say, the X direction expanding and shrinking, and the other vibration mode where this happens to the Y axis. And what happens in this case is that if I excite this mode, and that mode should be very close in terms of resonant frequency because it's the same structure. I made sure that I kept it symmetric. I should not really have that much of a mode mismatch problem. And this was made and actually has good performance. This is another example of a similar idea. Capacitive detection, of course, for the detection of the movements and also excitation. And this is one other example. This one is one of those rotating wheels type devices. Analog devices, again, we have the single chip solution from analog devices. I put a cap to protect my MEMS from the environment, but all of the electronics and MEMS are made on that bottom chip. And trends for accelerometers, well, one of the first things is that everybody wants them to be smaller and smaller. You have them in your smart pens, you have them in your smart watches, you have them in smart anything, right? In earphones and everything, right? So you want them to be smaller and smaller. Nowadays we are talking about millimeter by millimeter, a couple at most. And in some cases people are skipping the package altogether. So they get a die, the die that you saw in some of those packages. There's a MEMS die and there's an electronic die, and they give you that bonded piece of silicon. So they have MEMS and electronics as a piece of silicon. They hand it to you in order to make it easy for you to solder it onto your, let's say, PCBs and all that. They put some solder bumps on the top of the silicon, but that is it. There's really no package. We are trying to get deeper and deeper into silicon. Remember, a lot of these technologies depend on capacitive transduction, so we want to have narrow and deep gaps. The trends in improving DRIE processes are helping with that. We will have, well, some consolidation between the players, and then some new ones are coming along with new offerings. The new thing on the block is that we want to have high performance accelerometers for seismic detection or for gravimetry, so where we can measure the gravity with, let's say, 6-7 digits of accuracy. And what that tells you is that if I have, let's say, a chamber of gas underneath my feet, or a nickel mine, or just regular rocks. This is important for what we want to do mineral exploration on Earth, or if we want to do exploration of moon and other places. We want to see what is behind, what is underneath our feet without really having to dig. As is, we still are benefiting from having a two-chip solution. Most players are doing it that way because you have the best from the MEMS part, you have the best from the electronics part, and then you pay a little bit more in order to bring them together. People are going about using the electronic chip, for example, as a cap chip for your MEMS device, for your MEMS chip, so that you save a little bit on space. But even analog devices, which was a pioneer in the field, is moving towards a two-chip solution for some of their high-performance devices. And foundries like TSMC or others that are around and they can make your MEMS device provides the opportunity for newcomers. So if you have a great idea for making MEMS accelerometers and there is a demand in the market for your idea, it's now easier than before to have it made by somebody from outside. So from that point of view, things have become easier, but on the other hand, a lot of smart people have been thinking about these problems for decades now. So if you have a great idea, there is an opportunity. So that's that. The next lecture, we'll talk about some other MEMS devices that are fairly common nowadays, including RF MEMS and similar devices. And finally, that will be it for our MEMS discussion, development, design, and beyond that we'll move towards the application of MEMS. So discussion will be on interfacing and then later on signal processing for the signals from these devices. Thank you.